post to you guys? I posted several problems actually showing the antenna patterns. Did y'all get those?
That was when I was telling you that we have.
Did they post? Okay.
The one from 13? Or is it
I think it's 14 that you got. It was just something where I did this in Math-CAD. You can do it in MATLAB. It's just to show you the type of antenna patterns. I'm going to go over some stuff today. I want to catch us up, and what I'm hoping to do is get to the Friese transmission equation, but I got several things to go through. All right, first is with monopole antennas. There's a monopole is really just like a dipole, only there's no radiation below the horizon, all right, because you always assume a ground. Now, monopoles are used all the time. Most, if you look at any kind of standard FM broadcast or even AM, they just have one solid antenna going straight up, and they have the image of that goes down. I got to kill this camera here. Hope it goes off. So here we go. This is sort of a recap of things you need to know. This is going to be for monopoles, monopole antennas. Now, what I'm talking about is this. You're going to have a ground here. You have effective length here, L. That's the monopole antenna. It has a current I, just like the dipole. Now, you know, if we talk about this, we're going to talk about the two. I'm going to do it where I talk about a short dipole, monopole, the differences and similarities. So if you have a short dipole versus a monopole, all right, the dipole has a length L, has an assumed current I, right? This would be the current right here, actually, as it's coming in, assumed current I. For the monopole, it just has a length L. It's over this ground, but there's an image current right here. This has a current I as well, going up. And the total effective length here would be 2L. Everybody follow me? All right, now, if you come out here and you look at the electric field from a short dipole at an angle theta at a distance r, the electric field, this is assumed it's in the z direction, by the way. I'm trying to be consistent with how the book lays it out. So it's assumed in the z direction. The angle is theta. It's measured off a distance r. By the way, did a whole bunch of people go down to a Florida game or something? I don't know how many dropped. I actually don't know how many dropped. They may have, but I think a lot of people went down to Florida. That's what I was told by Bobby Woodard.
I know what it is.
What?
It was midterm week and everyone just kind of took Friday off.
I was about to say, I think that barrage of tests that just came through this last week just ended
I see.
control systems this morning, so some people might have just decided.
Slept in. I understand. Well, I do understand. I was told by Bobby Woodard, he's, I think, the vice president for student affairs, that a ton of students were going down to Florida. So he said, expect the attendance in your classes to be down. Well, he's right in this one, regardless of the reason. All right, now the E field from this, and this is stuff you have to know this one, is going to be J eta beta over 4 pi. Then there's the quantity e to the minus j beta r over r. R is just the radial distance in meters, but the angular variation is the sine of theta. That's the same for both. The E field over here is the same. For a short dipole, the E field is going to be the same. Here's the, oh, I didn't put this in here. This has a length L here. All right, I'm saying this has a length L for the antenna. Over here, the effective length is 2L. So that's the difference for the E field. It's J eta beta I, but then it's 2L, where L is the length of the monopole. Follow me on this, class? Yes, sir. It's the length of the antenna, and because the monopole has an image down here, the total length, right, is 2L. Here, the length is just L, the length of the antenna. No, that gap's infinitesimally small. Normally, they assume that when you drive an antenna, the distance between the upper and lower portion is infinitesimal. What's that? This is here, yes, yes, you're right. It's Jn beta I times 2L here over 4 pi, and then it's e to the minus j beta r over r, and still the sine of theta variation. It's in the a phi direction. They're both in the a phi direction. The only thing I'm saying is the only difference in the E fields from either one is that has a distance of 2L, right? If the effective length of the monopole is L, the length with the image would be 2L. Do you follow me? All right, that's the only difference. They're identical otherwise. When you come here, the directivity for this is for a short dipole, would be 1.5 times the sine squared of the angle theta. The directivity for this doubles, and here's why. The power is only radiated in half the region. Everything below the horizon, there's no power radiated. So if you think about the actual formula for directivity, where you take 4 pi divided by the integrated normalized power pattern, that normalized power pattern is only integrated over half of what it was before, so you're going to effectively double the gain. Over here, your gain, or I should say directivity, is going to be equal to 3 times the sine squared of theta. Now that's a difference. And whatever it is for a dipole, the gain doubles, or the directivity doubles. Effectively, the gain too. Follow me on this? Another thing, the thing that really changes here, the radiation resistance for a short dipole was equal to 80 pi squared, and it's the length over lambda squared. Now that's in ohms. Here, the radiation resistance is halved because it's only radiating into half the area. Follow me, or half the volume. So over here, the radiation resistance, I can put it here, R rad is equal to, and you can just put, you could put R rad of a short dipole divided by 2, but it would be equal to 40 pi squared. And now the length is going to be, well actually, the length for this one, that will be 2L over lambda squared. Now remember that length, that L there is for the monopole. Maybe I should put it L sub m, so you understand L sub m is only for the top part, right? Not the image. Well, here's the problem is, I'm talking about if this is L, and then we use this as L because it's a fact, then you're going to see that the radiation resistance is half for that same distance from here to here. Follow me on this? But because we're talking about just this length here, then you have to put 2L there. Okay? That's the reason I did that. All right, that's the radiation resistance. Finally, if you want the H field, you just take the E field divided by eta. That's it in magnitude. Got it? Now that's short dipole and really short monopole. If you do the half wave dipole, the only thing that changes now, we'll put lambda over 2 dipole. Here, again, now I'm going to be talking about something where I have a length L here, and now lambda is, or you could even put long dipole, but I'm going to put lambda over 2 dipole because this is the most common one. Now when I come out at distance r at an angle theta, I have a current I here. I know my E field for the half wave dipole would be equal to j times 60I over r times e to the minus j beta r here, and then it's times that angular function cosine of pi over 2 cosine of theta over the sine of theta. If it's something not a half wavelength but it's a long dipole, then you put in the full angular function here. Do you remember it's cosine, and then it would be beta d over, it's really beta d over 2 times cosine of theta minus the cosine of beta d over 2. But I don't want to, I'm just trying to give you some of the things that is common you encounter this. This is what you're going to encounter typically. That's the E field for a half wave dipole. The radiation resistance for a half wave dipole is equal to 73.2 plus j 42.5 ohms. Now that's if it's exactly a half wave dipole. Yes, sir? It's cosine of pi over 2 cosine theta divided by sine theta. If you look in the book, it's the formula for the half wave dipoles. And remember, Stu likes putting in the power. If you want the power for either for this over here, the only thing you do is take this, square it, right? The E field squared divided by 2 eta. I like the E field because that's measurable usually is what they measure. Typically, they sometimes measure power. Now that is for an exact half-wave dipole. So write this down, put L exactly equal to lambda over 2. Typically, you can also get R rad equal to about 73.2 ohms plus J nothing if L is equal to 0.85. Well, I'm sorry. He has it 49, my bad. 485, pardon me, 485 lambda. Then you just get this. You'll have the same exact gain, and I'm about to put that down. Remember I said about shortening a dipole from an exact half wave just down to something slightly less than that, 0.485 lambda, and you'll get rid of the reactive component. It's important because now you don't have to impedance match. All right? There's no reactive component. Then finally, the gain for this one, or the directivity, I'll put it right here. A directivity is 1.64, and then it's times the cosine of pi over 2 cosine of theta divided by the sine of theta, but this whole thing's squared. Right? Now you take the angular function and square it. It's still, the nice thing about this half wave, the maximum value of this thing is 1. That's what's nice. So you don't have to, when you're doing the normalized power pattern for this, you just can use the cosine of pi over 2 cosine theta over sine theta if you need it. It's already normalized. You just get rid of that magnitude right there. Okay? Next, when we do the dipole, or the quarter wave lambda over 4 monopole, now you got this, you just have an antenna like this, where now this is going to be lambda over 4. Before, this L right here was lambda over 2. I might as well just put it in, it's lambda over 2. If that's lambda over 4, and this is the ground plane, coming out, if this is a current I, electric fields are going to be the same, except, well, actually they're identical. If I'm out here and I want the electric field, just like I had the electric field out here, this electric field will be equal to J60 times I over R e to the minus j beta R times the cosine of pi over 2 cosine of theta over the sine of theta, a theta direction. It is identical. There's nothing to adjust. The thing you have to know is make sure it's a quarter wave long and make sure you know the current, and that's it. Now, that's the E field. I also, from this, I can go ahead and say that the radiation resistance here will be equal to exactly half that. So it's going to be 73.2 plus J 42.5 divided by 2. It's exactly half. And if you chop this one down proportionally, so it's effectively going to be this length by 2, follow me on this, then you're going to get half that. You would get just 73.2 divided by 2 ohms. Follow me, class? In other words, what we're really doing is the monopole is identical to the dipole in terms of its radiated field patterns. The radiation resistance is half, the directivity is double. It's the only thing you have to remember. And you've got, now over here, for the directivity, now it's 2 times 1.64, and then it's times that angular function cosine of pi over 2 cosine of theta divided by the sine of theta, all squared. You just take, it's really the same exact thing as down here, but you're putting a 2 in front of it. And that's really the monopole versus dipole for the typical ones. You could do it for the loop antenna. I'm not worried about the loop antenna or anything like that. It's the same effect. And you'll see this used all the time. Typically, broadcast antennas, most of them, not all, most broadcast antennas for AM, FM stations, they assume the ground has an image like that. And just for the record, so some of you will be doing this. I had a second class FCC, I think I still do, second class FCC license, and allowed me to be like a radio station engineer and stuff like this years ago. One thing you're going to learn, practically speaking, if you are going to deal with an antenna where you're going to have an image and you're going to be broadcasting a lot of power, you don't want many losses in the ground. You'd like the ground to look just like a perfect conductor. Well, that's not feasible, but what they'll do is, there's about 3 things they do. One thing is, if it's real arid, they go get cross-hatched mesh, and like you see put down the metal nettings and stuff when they pour cement, stuff like this. Well, they'll get something like that, but they'll make sure that the space, the length between of the square pieces is less than 1/10 of a wavelength or less. It's all right, it has to be that or it won't look metal. Then they'll bury that thing maybe a couple inches below ground, and that will effectively emulate a ground, a pretty good ground connection at the frequency you're talking about. The second thing they do, I don't know if it's legal in Alabama, you can buy a thing called copper sulfate. Does anybody know what that is? You know what a water resistor is? Anybody? All right, here's the thing. Some of you will be involved in this at some point. When you have anything with that stores a lot of energy, like large capacitors that are going to be part of a system, when they get charged up, if you want to go in there and do anything, you want to safely discharge them. Well, electrolytic capacitors, you can't just short out. They'll blow up. Do you know what electrolytics are? All right, those are they're polarized capacitors. They can store a lot more charge with an electrolytic, a lot more energy versus a normal dielectric, but they're polarized. And if you try to short those and send current the wrong way through them, you might say it that way, they'll blow up. I've actually been over to the Space Power Center, and I remember years ago when we had a railgun project, they showed me what a blown up capacitor looks like, and it literally is a grenade. It may kill you if you're too near, so you don't want to ever have that. So what they do is they make a water resistor, and they get tubing, thick plastic tubing about that long, and they get about this much of it. It looks like surgical tubing, only a lot thicker, right? And they fill it with water. They put a cork at one end, put a cork at the other end, but when they fill it with water, they put copper sulfate in there. What that does is make it pretty conducting, like of the order of maybe 30 ohms, 40 ohms, and there's recipes for this, so for the amount of water, how much you add. Now you've got a water resistor. The thing about water is it takes an enormous amount of energy to heat it 1 degree. And so water is the ideal thing if you need a resistor that can dissipate lots of energy fairly quickly without boiling or heating up and burning up. That's how they do it. It's called a water resistor. You can look it up. I learned a lot doing that railgun project, and this is one thing. And then you would take that with a special hook. If you had 10,000 volts on a capacitor and you needed that thing to be shorted out so you're going to do some work, then you would take that water resistor, put one into ground, and go over there with a hook usually. On the other, you tie a wire to it with use a solid piece of grounding rod. Don't ever use this hollow aluminum, because when it starts shorting out, can actually it can burst. It'll heat up fast and can blow up. And a physics prof I knew him years ago almost lost his eye because of that. He tried to use it's called a chicken stick. Try to short something out, a capacitor, with one of those things, and it turned the aluminum to molten stuff, and then went to vapor and almost took his eye out. I'm very cautious about this. Anyway, if you take that water resistor, that's going to limit the current. It's not going to go, and it will also, it'll decay slow enough over about a minute or two so that there won't be any reverse current in the capacitor. I'm telling you this because if you work with radio power and stuff like this, large power and stuff like this, you always have to encounter these large capacitor banks. And most of the time, when I was where you were, nobody told me about this. So if I go there and I'm doing a project and just reading through or connect the capacitor, then I need to discharge it. If I do the standard thing I did when I was where you are with labs, you want to discharge a capacitor, just short it out. Huh? With a screwdriver or something, you do that over there, you'll kill yourself.
Elaborate what you're talking about with it exploding because of the reverse current. I thought it would be due to the internal resistance causing.
Well, it does heat up, but the problem is when you have a polarized dielectric, all right, this is something where everything's aligned one way. Now when you drive current in there the other way, they try to flip like this, and then when you do that, frictional heating, you're right, it is thermal heating, but it'll blow up. It's sort of like a microwave kind of. I put it to you this way, electrolytics, I'll work around in TVs and stuff, and I have no problem, I'm not worried about them. Large electrolytic energy capacitors, I will not mess with those unless I know for sure that they're not charged, and if I have to discharge them, I'm going to do it safely. So that's my take on that. But I like saying stuff like this to give you a little insight, because most people, when they take electromagnetics, it's not really, even though this is an applied course supposedly, we don't have an antenna lab. If you take Riggs's course in antennas, you get it. And you go out there in the real world, not aware of some of the dangers. A lot of antennas, high power antennas, especially if you're around radar, long range radar, or high power broadcast antennas, don't get too near to them.
Actually, I was working with a wireless company and we were setting up some system for a stadium. We had antennas and they were sending out like microwaves just about, so they had like a 12-foot safety compliance. If you got any closer, they would just like cook you.
This is something, a lot of people don't know this. So you're gonna be working around Atlanta Airport, right? Somebody's gonna be doing some work, you got a job to do. Well, Atlanta, it has legacy radars. They're rotational radars that they're megawatt peak power, right? If you go up there and that thing hits you in the face, it may blind you or burn your retina typically. It's horrible the damage you can do. I've heard this, it's hard for me to believe they do that, but on this carrier I was on, the Eisenhower, if you take dielectric rods and you put hot dogs on, you put them up there and cook them. The problem is when you do that, you're scattering the Emag right into you. So not only can you cook the hot dogs, you might kill yourself. But I've heard they can do that. I've never done it. I wouldn't even think about doing that with a live radar with an antenna. But be careful around any high power antennas. That's one thing I'm going to caution you. Namely, your eyes go. I don't know if you're familiar with this, but microwave energy is horrible on your eyes. You can blind people if you're not careful around high power. I don't know if you worked in a wireless, high power microwave area?
No, it was, they set up like antenna systems for like
yeah, but
larger
microwave
concrete
length is
buildings.
powerful. If it's over 150 watts, was it over 150 watts?
I don't remember.
Well,
Probably not.
be careful. That's all, I guess what I'm saying. Be careful. So, that's sort of it for monopoles. I only care about the short and the half wave, to be honest with you. And most of this is for arrays, when we deal with arrays. So, now, I talked about arrays, I gave you some problems with arrays, and I want to show you, practically speaking, what I expect you to know. Come quiz time.
Let's go to the next Friday, right?
And maybe sooner than that.
We're not here on Friday. It's fall break.
That's the reason it might be sooner, or on fall break. Unless there's something that's happening that I don't. We're off Thursday and Friday, aren't we?
Yeah.
Maybe on Wednesday. Now the next thing I'm going to show you is, this is going to be for arrays, and I'm going to show you how to do an array, a typical array. All right, first the arrays we're talking about are arrays where we have a constant space in between elements. So let's say we're going to have, I'm just going to say they're short dipoles, and they're going to be spaced let's take 4 for now. They're spaced a distance d apart. So we've got 4 of them, they're spaced a distance d apart. First one has got a current I naught. Second one, I naught e to the j alpha. Third one, I naught e to the j2 alpha. And fourth one, it has a current I naught e to the j3 alpha. So I'm saying that I'm going to create an array evenly spaced, vertically oriented, short dipoles, all right? Now, I want to tell you this. To get these currents is no small thing. Here's why. It's not the phase, it's the magnitude. There's an impedance interaction between this one and this one, this one and this one, and this one and this one. It means the driving point impedance of this guy is different than this guy, is different than this. Well, these two will be the same, and these two will be the same. But the impedance is different. So in order to get that current, constant current, they have something called a power coupler that we'll talk about later if we have time. Remember that. If you build an array and you put a voltage with just a phase difference, increasing phase difference like I'm showing here, you will not get the same current. You have to have a power coupler to generate to cause that to happen. All right, that's important. But we're assuming we do, so we have these currents. Now, what we're going to do is, if we say these are short dipoles, right here, And I want the field from the center of the array out here at some angle. Now remember, if this is the z-axis right here, call that the z-axis, then this angle right here would be theta. Y'all with me? There's a second angle we worry about. Well, first for this one, if this is a short dipole and it's measuring with respect to the z-axis theta, then I can say the E field from a short dipole, this would be from the element, the short dipole, would be J eta beta I over 4 pi times e to the minus j beta r over r, and then it's going to be times the sine of theta. It would be in the a theta direction. So from a single element, we know that's the field, right? Are you with me? For a short dipole, I'm going to say I got 4 short dipoles with that progressive current. Now to get the antenna pattern caused by this, the total antenna, this would be for the E field, E total for the array, would be equal to the E field of the element that I just put up there. And remember, this angle becomes critical. Theta is measured from the z-axis over here, times the actual E field of the array. You could say it's the array effects. It's these two. This is the way it appears in a lot of books. Well, the element we got, it's J eta beta I over 4 pi e to the minus j beta r over r, then it's times sine of theta. Follow me? That's just the element. Now, what is the array? Remember what I put down. For the array, what you're going to get is this. You're going to have the sine of n psi over 2 divided by the sine of psi over 2. Here, psi is equal to beta d cosine of phi plus alpha. Now, alpha is just the increase in phase, right? If it's 30 degrees, first one's 0, next one 30 degrees, next one 60, next one going to be 90. Follow me? If alpha was 30 degrees. Are you with me on this, class? Now, this is important. Beta is 2 pi over lambda. And d oftentimes is in terms of fractions of lambda. All right? Usually, if you set the spacing here, if d was equal to lambda over 4, as an example, then d here would be lambda over 4 cosine, and I got to do one thing here, plus alpha. Now you'll notice that this angle, when I talk about cosine alpha, alpha is phi is the angle that the radius vector r makes with respect to the array. Are you? Because we're shooting out at this angle, right? We're at a distance r away at this angle. But this angle used in that equation, right, from here to here, so it's equal to 90 degrees, or really pi over 2, minus theta. So what you do is make sure you do this right, too. So this is going to be equal to either 90 degrees, right, minus theta, if it's in degrees, or it's pi over 2 minus theta if it's in radians. Does everybody follow me on that?
And we're assuming that angle's constant for the whole array.
Well, you're so far away that there's no change.
So if you were closer, you would consider it different.
Well, if you're real closer, then this wouldn't. The minute these aren't parallel arrays, everything falls apart.
Okay.
You've got to assume that they're parallel, so we have to be a long ways away. That's the critical thing here. We're not up close to the array. But this is how you would get it. And if you add alpha phase change here of 0, then it would just be this equation right there. By the way, cosine of 90 minus theta is equivalent to the sine of theta. All right, if you want, you can do that. But I'm putting in to make sure you see the angular variation. It's always the cosine of the angle r makes with respect to the direction of the array, the orientation of the array. That'll get you it. Now, I did some problems. I don't know how many tried this on MATLAB. I could probably do it with MATLAB too and show you. MathCAD's a little quicker for me to do it. But if you do this, here's what ultimately happens. Remember this part for any kind of a question you have on an exam or something. If I take a look of just the E field, the normalized E field pattern from an element, oriented this way, in the z direction, I know it's proportional to sine of theta. So this would be my angular variation of the element. You follow me? For a short dipole, right? That's how the E field would vary versus radial distance. That's a polar plot. Does everybody see this? Now, what happens if I want the total one? I take this pattern times that of the array. Now, with the array, I know my array is this way. looks like, I'm not sure yet. But if the array had this pattern, I'm going to just say, suppose it had this and this. I'm trying to show you this. Now what you do is when you multiply these two patterns, listen to me, I'm going to multiply these two to get the net pattern. Now here I can see I've got a null, vertical null there on this one. Vertical null times anything is still a vertical null. Got me on that, class? Because I've got 0 radiated up that axis, right? Even though here my array looked like that, the pattern, when I take this times this, it would still have a 0 there. So I know it directly up, I got a 0. Now, the thing is, if I'm going up, I would take literally, I would take the length of this vector at any given angle times whatever it is here, you know, the length of it here. But I can see that really I have very little, if anything, there, times something big there. So really I get this. I get sort of a thing like this. And then I've got a 0 there. So it's going to come back like this. I'm not drawing this real well, but I'm just saying there's very little to there. Now this is the main load. It's the strongest. Times this, it's going to be multiplicative, and you're going to get a huge pattern that way. And then you get some other ones over here because it's almost always symmetric about the vertical axis. I'm just trying to show you the way you would think about a sketch like this. I'll give you some problems that would be representative of what you're expected to do, and I'll show you more later. For this particular one, the hard part is not this, not the E field of the array or of the element. It's this right here. That's the one you have trouble with seeing. And frankly, I probably won't go, if I ask you to sketch anything, it won't be more than 2 elements probably, maybe 3 at the most, but I'm going to give you something to work with so you can see how you can sketch these things quickly. All right? I'm just trying to show you how you literally do it. You think in terms of multiplying this times this. And if I had a question, how much power is radiated in the z direction? Just by looking at this, you know it's 0, right? Where is the maximum power going to be radiated? It's going to be at 90 degrees to it. Now here's some terminology that you have to get used to with antennas in general. When you have an array of antennas, regardless of what the array consists of, they could be patch antennas, they could be loop antennas, short dipoles, it doesn't matter. When you have an array, they always talk about the vector direction of the array as the key thing. If the main beam, and the main beam in all antennas, you're going to have a normalized antenna power pattern or E-field pattern that is maximum. It has the largest value. If the main beam, and it has a certain beam width, is perpendicular, if this would be the antenna pattern, that's called broadside. It comes from an old naval term. When ships went to fire on each other back in the days, the Spanish galleons and stuff like this, they'd always come so they'd bear all their guns, and it's called broadside. If you're shooting, if your main beam is perpendicular to the actual axis of the array, it's broadside. Now, so that's broadside. The other thing that happens is it's called in-fire. And if we phase these, right, specifically if they're phased so that either this is going to be, so that the phase difference between here and here, looking in that direction, is 0, if that's what it amounts to, then you're going to get this. You're going to get a main beam like that, and a couple of side lobes, but this is called in-fire. So if the main beam is shooting out the ends of the array, that's called in-fire. That should make sense. Those are the 2 things that are most common. Yeah?
So to vary those things between in-fire and broadside, are you mostly to change the element field?
The only thing you need to do is change the phase, and you can go from broadside to in-fire. If you change the phase, remember that's the one thing electronically, we can easily change the phase of that. I mean, if the progressive phase shift on each one of these, we're assuming we have the same current, all right? So, and the same spacing, so you can easily change the phase. Remember, if in that direction the phase difference is 0, you're going to get multiplicative behavior, right? And if you have phase, you know, if they're all driven at 0 phase, then all these things will have a maximum the broadside pattern would happen because the main power load would be in that direction. If there's no phase difference, just think about 2 things that are radiating, right? If there's no phase difference, then if you're going straight out from them, there would be coherency, right? And if you're going perpendicular, then whatever the distance would times beta would be the phase difference. And if that was 180 degrees, you get a null that way. I don't want to spend a lot of time on this right now, but I'm just going to give you an appreciation for this. There's another term you're going to hear over and over again. It's called the bore sight of the radar or the antenna. Bore sight is in the main beam. If you look at that, the way it's directed is called a bore sight. For instance, if you have a standard type of parabolic dish antenna, bore sight is perpendicular to the dish. If you have a dipole, like this short dipole, they don't even usually use the term, bore sight would be perpendicular to the length of that dipole. Got me on this, class? That's the terminology that you have to be aware of. And it's just sort of to bring you up to speed when you're reading some of the problems in his book. Now, I mentioned this thing about doing the antenna pattern. Really, this is later on when we get to microwaves and connecting antennas with microwaves, we'll probably revisit this and talk more about it in detail about what's important in the real world. And almost all, not all, but almost all modern day antennas used for the military and any kind of expensive, let's say, commercial aircraft, they're patch antennas, and the reason they use patch and not discs that rotate is because they can steer that beam anywhere very quickly electronically. They can literally track 5, 10 targets all at once, and that thing will just scan around very quickly. The legacy antennas, if you all saw old World War II movies, even now though, some ships have, they have these rotating parabolic dishes or rotating planar arrays. Those things rely on mechanical speeds, right? And they can get long periods where there's dead space. You don't know what's out there. Think about some of those things. Well, some of these missiles come in. I was told this, that the Chinese now have a missile that is doing over a mile a second. All right, well, when you have a sea skimmer coming at you that fast, you can't pick it up on a radar until it's within probably a couple miles, right? If it's a mile a second, think about that. A legacy radar turning could easily take 10 seconds to do a revolution, easy. So that's why nowadays Aegis class cruisers, almost everything have very high speed array antennas. They're not just 1D, they're 2D array antennas, and they have very, very narrow beam widths. They can track targets. Quite frankly, it's amazing how much they can do so fast. I mentioned about that because that's one of the areas I'm interested in my research.
How is the current phase offset? Like electrically, how is the current phase offset to steer the beam?
How do they do it?
Yeah.
Well, there's a lot of ways. You can do it literally. If you think about this, when you have a signal coming out, right? First, if you're talking about just you have the same input impedance. If you want a different phase, well, phase has to do with what? The length of line that a signal travels. So if I have two antennas, and I want this one 90 degrees different from this one, I have a signal here, right? I come out, and now I make the length of line on this one longer by 90 degrees or longer by pi over 2 radians. Beta is going to be the actual radians per meter times the distance. And what they'll normally do is, on a lot of these, if they're feeding antennas, what they'll do is they'll have links that are exactly 1/8 of a wavelength that they can turn on and off with MIMS circuits. So if they want 1/8 of a wavelength difference, right, they turn one on, and so the signal has to go back and forth 1/8 of a wavelength. They want two, it'll go back and forth, and they'll just do that. That's a cheap way to do it. There's some sophisticated ways where you can literally have generators where you have the same frequency on the generator, but now you can adjust the phase of one compared to the other by just microelectronic circuitry. That's another way. That's a little more expensive. And then there's something that's the most expensive, but it's also the best, and that's where they literally do exact time delay. And what I said was when they add length of lines, that's time delay, but there's a way to do this electronically where they take whatever the signal is that's going to feed the first antenna, and they literally take that signal. Now, this is going to be with FPGAs, all right? So they get an exact memory of this after it's sampled at twice the highest frequency of interest. Then they take that and they literally shift it back by any amount of time you want. So that whatever appeared at t equals 0 will appear at t minus the time delay, and then you can feed the time delay to the next one. That's a little advanced now, but I'll tell you why that's so important. Because If it's just the phase difference in the signals that you're transmitting, when you're transmitting it out there and it's hitting the target, reflecting, and coming back, well, an enemy can spoof that, but he can't spoof a signal where you're getting some signal, and whatever that signal is feeding one antenna is exactly time delayed by another to get a wave that's going to be constructive interference and stuff. They can't spoof that one, but that's something we'll talk about with radar. All right, we're not there yet. And some of that won't make a lot of sense until you see it applied.
Do those work at like a certain band or anything? Or
Huh?
do those work at a certain band, like K band or Ka band? Or what's the most common one?
For radar,
Yeah. Do those work at any kind of band? or anything?
typical radar, long-range radar is around 1 gigahertz in that range. It's because the higher the frequency, the faster the signal attenuates. So typically you get even down to 500 megahertz. A gigahertz is a long range. 1.4 gigahertz is typical for a lot of long-range navigational radars, that kind. The 10 gigahertz from really 8 to about 10, 6 to 10 gigahertz is X-band. Actually, it's a little different than that, but it's roughly the operational band. X-band is something that gives closer in target acquisition, more resolution. I can see something the size of that screen square coming at me. Then there's K-band. Now there's a variety of K-bands. The police around here use K-bands, about 32 to 33 gigahertz. That gives them the ability to differentiate between your car and the car next to you, right? Because it's got a very narrow beam and stuff for the type of antenna they use. And they can do that with K-band. They can't with X. They used to have X-band all over the place. Down here they use K. Up north you'll see KU, which is about 18 gigahertz. Beyond that, and again, the higher the frequency, the smaller the target they can actually resolve. And when you're talking about incoming weaponry, it's always a trade-off. You want to be able to see typically the front end of a missile. Well, that may only be that big, right? And we'll get to what that looks like, how you figure out the electrical area of that. But you want many wavelengths across there. So you're going to have to use high enough frequency so you can see the thing, all right? But you can't use too high a frequency where the thing will just die out before the signal reflects back. And there's all sorts of trade-offs. Peak power versus the amount of time between. Usually you have radar's on, then it's dead. Radar's on, dead. Well, there's all sorts of trade-offs in there we'll talk about. And there's algorithms for figuring out the best way to do it. Right now, I'm getting to the point I want. I only got 4 or 5 minutes. This is a freeze transmission. This one you'll appreciate, you'll see it useful. It's called freeze transmission equations. And this one, I go back to the way I typically do problems in radar and in antenna design. Now, we're going to assume that we have an antenna. This is the way I draw antennas when I teach radar. This is the way the book does. And here, I'm going to say it's a certain amount of transmitted power in watts goes into there. This antenna is going to have a certain gain, right? A gain G. And that means if I come out a distance R away, now remember that gain can be a function of angle too. All right, we'll just leave it. R away, I can say the actual transmitted power density, that would be PF in watts per meter squared, would be the total power transmitted over 4 pi R squared. Now that's like if the power is just spread out isotropically. Take total power and divide by the surface area of a sphere, right? Then the gain sharpens it. So if I multiply it by the gain here, the gain of the antenna, and put gain of the transmitter here. Now I know the power density. And that's from before, right? Now what if I put an antenna up here, and this is going to be the receiving antenna, and it has some G in the receiving antenna. Well, that doesn't mean anything to me to figure out how much power is going to be actually absorbed by that thing. The thing you need is the electrical area. Write this down. It's called the aperture. It's how electrically big it is. And the aperture of an antenna, we can prove this later, the aperture of that antenna will be equal to lambda squared over 4 pi. Now that's free space lambda squared, or it's the lambda in the region that the signal is propagating in, times the gain of the antenna. In this case, the gain of the receiving antenna. And that's in meters squared. So if you think about it, if we have a gain of a short dipole, that's 1.5, right? 1.5, and say our wave, it's 300 megahertz signal, so the wavelength would be 1 meter. If I had that and I wanted to know how big it was electrically, I'd have 1.5 over 4 times pi, or roughly 13, somewhere in there, a little more, 4 pi. So 1.5 over that is less than 1/10 of a meter squared. It's small. Do you follow me on this? But still, and people get caught up in this. They say, well, when it's a thin wire and this long, it's just the diameter times the height. And that's not what the electrical area really is. At very high frequencies, it turns out to be the physical area of the antenna, and when you have many, many wavelengths that cross the diagonal. But for these, the electrical area is found by doing this. That's how big it looks. That means the power received here, if that's how big it looks, P received by that antenna, it's not the actual power that you can use, but the total amount of power received by this antenna would be equal to the average power density. Remember, power density here is in watts per meter squared. It's that times the effective aperture. Well, that means it's going to be transmitted power times the gain of the transmitter over 4 pi r squared. Now that's the transmitted power density. Times the aperture. Well, the aperture is lambda squared over 4 pi times the gain of the receiver. And that would be the power received. Just try to appreciate the only thing I've introduced now is the concept of an electrical area, which is lambda squared over 4 pi times the gain of the receiving antenna. You follow me in this class? Which means if we have a link, and now I'm going to do it here. If we just have a link here, and we have a transmitting antenna, and we have a receiving antenna, and we have a distance r between them, and we say we're transmitting the power PT, and we want to find out how much power is going to be received here. If you look at this, P received here is equal to the gain of the transmitter, gain of the receiver, always that. Then the term lambda over 4 pi r, right here, squared comes in. Now, I can do that by factoring out the 4 pi, or the 4 pi and the r and the lambda and then squaring it. You can see that they all appear here, squared operators. So this will give me P received over P transmitted. And this is important. And that's called a Friis equation. Now that P received or P transmitted is something that talks about, you could say it's the goodness of a microwave link. That's another way of thinking about it. Because a lot of times what you're trying to do is get a figure of merit for how well an antenna system is operating in terms of transmitting power between one, say a microwave dish linking 2 cell phone towers. Y'all seen that, right? Well, that will give you a measure. Something to note, this gains here are not in dB, they're linear. So if you have a gain, you know, a 20 dB is what? That's 100. 100, right? So if you have 20 dB antenna transmitting, 20 dB antenna receiving, you'd have 100 times 100 or 10 to the 4th. You're following this? Now, how far away are you? I don't know. But basically, then you would multiply it by lambda over 4 pi r squared to get an idea of, and I use the word goodness, but it's an effective measure of how well your antenna system is linked to the other. And it's a lot of times for microwave communication systems, things like this. But the Friis transmission equation allows you to know how much power any given antenna you're going to create can receive. And I'll get to more on this next time. All right. And I have got a lot of pain right down my back, so I've been wincing. That's the reason.
Why is that from the gym?
Now I have a core, large muscles below the trapezius muscle.